All right, welcome to part two for 404 orthonormal basis and the Schmidt process. What we're going to look at very briefly, it's going to be a pretty short video, is projections of an orthonormal matrix and how it simplifies projections onto the subspaces. And so when we look at our equations, if we're trying to find that projection matrix and figure out what all those projections can be, what happens, and then we'll kind of run through an example of that. And so again, what we're assuming is that when I look at my list of n vectors that are independent, instead of referring to them as a1, a2, all the way down to an, we are going to assume that these are orthonormal. So we're looking at q1, q2, all the way down to qn instead. And if I do that, that means instead of a matrix A that would contain these vectors as columns, we now have a matrix Q that contains these as columns, where this matrix Q is orthonormal, that it would fit the dot product definition that we had up in the previous part. But not only that, even if we assume that M is greater than N, that this is a rectangular matrix, QTQ is equal to I. And we saw this in the last part, and talked about in the last part, that if I do this multiplication, we're going to create the diagonal matrix specifically with ones along the main diagonal. That creates I. Again, when I do that, that's going to overly simplify our problem here that QTQ, its inverse, that's just the identity matrix. And so this becomes Q transpose B. So much easier to solve for X hat. My projection of B onto the subspace Q is just QX. And then here, my permutation matrix that will project any vector onto my orthonormal basis that we have is now QQT. And again, this may or may not be I, it just depends on this inequality. Because we're assuming right now that this is rectangular, then that's going to be another matrix, P, not the identity matrix. And so our formula is much simpler. We don't have any inverses that we have to worry about. And what you'll kind of find is that trying to find the inverse of a matrix is many computations. So just to try and help things along the way. Now, what I want to do is I want to look at the matrix multiplication that works here for Q hat based off of what we have, because this is what's going to kind of define how we take our vector B and we project it into its pieces that are on the subspace, so in this case onto our orthonormal basis, and just to see how we can then calculate that projection. So if P is equal to Q x hat, well x hat is QTB, so again my projection matrix that we're going to use to multiply with B is QQT. And if I think about what this multiplication is doing, Q is essentially the columns that we were just talking about, my vectors Q1, Q2, all the way down to Qn. And then I have my other QTB, which is Q1 transpose B, Q2 transpose B, all the way down to Qn transpose B. And so if we were to do this multiplication, notice that our projection, our answer is going to be Q1 transpose B, plus Q2 transpose B, plus all the way down to Qn transpose B. And this is equal to my projection. So in order to find my projection from B onto our orthonormal subspace, we need to calculate these multiplications. And again, because we're looking at Q1, Q1t, we are going to be calculating this almost like magnitudes in a way for each of these. So I want to show this through a calculation in particular, which is in example 4. He gives a square orthonormal matrix, essentially an orthonormal basis, and then projects, I believe, 6, 0, 0 on the next, let's see, Q 0, 0, 1, excuse me, 6, 0, 0 is something that we projected already in the last section. And so I just worked through that and just kind of talked through it so you can kind of see essentially how I would think through hopefully that'd be helpful. All right, so we have rows and columns are equal. So I have Q is equal to 1/3. I have a 3x3 matrix, -1, 2, 2. We have 2, -1, 2. And then 2, 2, -1. Now, I'm not going to do this, but as a check, you'll kind of see this listed if you want to check to see that this is orthonormal. If I do Q transpose times Q, we will get I. If I do Q transpose, we get I. So in both cases, since this is squared. So Q transpose is the inverse, both sides. And so what we want to do is end up finding the projections. I want to know what is Q, essentially what is P1, P2, P3. Finding those individual projections, and then if I add these three things together, this should give us the actual projection in our original vector. So we need to find the P1, P2, P3, because all of these would add up to give me B. And so we're going to go through and do that. So to find the first piece, P1, P1 is equal to Q1 transpose. Q1 transpose times B. And so Q1 is 1/3 of this. So 1/3 of this vector, -1, 2, 2. And then my transpose, Q1 transpose B. Again, I've got another 1/3, -1, 2, 2 with B, which is 1, 0, 0. 0, 0, 1. Here. All right, so I want to do this multiplication first here. And so just because this is going to give me a scalar, so -1, 0, 2, 0, this will give me 2. So this is 2/3. So I have 1/3 times my vector -1, 2, 2, times 2/3. So this comes out to give me a first projection of 2/9, -1, 2, 2. We can kind of confirm that. Looks like I messed up my math a little bit. Q1 is just that column, so no extra 1/3. So we have here, so just 1, 2 here, so 2/3 here. Apologies. So over here. Q1 being just the column. So then, if we do this for our second projection, P2, again, I'm going to have 1/3 just listed once. Q2 transpose, so Q2 being 2, -1, 2. And then we're going to essentially do this multiplication 2, -1, 2, close it with 1, 0, 0. Dang it, keep doing this. 0, 0, 1. Again, 0, 0, 2, so this is another 2/3. 2, -1, 2. And then if I do this for P3 as well, we've got 1/3 up front, 2, -1, transpose 2, 1, 0, 0, 1. Didn't mess up this time. And now we'll get -1 or -1/3. 2, -1. There's our P3. So we have our projection on the P3, our P2, which is here, and our P1, which we found up there. There's our P1. So just to confirm, we've got 2/3 times Q1. We've got 2/3 times Q2, and then we've got -1/3 times Q3. So notice how the original columns are still here from here. And again, you see that listed. And what's interesting with this is that if you were to add P1 and P2, so if I was to add this one and this one together, what that would give us is the projection onto the subspace of just those two. It'd be a plane, because it'd be two vectors out of R3, and then all of R3. And then if I was to take this one plus this one plus this one, we're finding the projection onto the entire space, which gives us the original vector back, which is 0, 0, 1. And you can see that in terms of the textbook. You can also see this in terms of the notes. But each time we're finding a projection onto a line, onto a plane, and then onto the entire space as we continue to add these. And we kind of talked about this a little bit with the projections, how when we're projecting onto a subspace, how we're finding each individual projection that when added together would result in our final piece. And we're going to kind of use that when we start working through the Gram-Schmidt process next. Because Here we're starting with orthonormal columns, but if you think about our projection section, A was linearly independent columns, but they weren't always orthogonal or orthonormal. We had to essentially find that orthogonality. And so what we're going to be trying to do now in terms of answering the question of how is if I take any linearly independent vectors A, n linearly independent, can we find an orthonormal basis for it? And then from there we can do our projections. So that's kind of the initial step next, trying to answer that question.